In our next example, we have another picture or graph to look at of a function. This time you're going to notice that we do have a constant interval, a flat piece. So I went ahead and copied the problem to the board, the graph to the board, and I've labeled the points. So we're going to call this point right here -1, 2. This x-intercept's at -1, 0. We have a y-intercept down here at 0, -2. This low point or trough or minimum is at 1, -3. We're going to cross the x-axis again at 3, 0. Looks like the maximum or this peak over here is at 3.5, 2, and that crosses the axis again at 0. So that way we all have the same values on our answers. Again, the very first question is the domain and the range. So domain, there's arrows on both ends. So it's going off on the left and off on the right. So we know that's -infinity. Part B, the range. That's the bottom of the graph. Well, this arrow on this side is down there at -infinity. The top of the graph is up here at 2, and it doesn't go beyond that, but it does include it, so we'll put a bracket on it. Next thing is the intercepts. So the intercepts, let's see, we've got an x-intercept at -1, 0. We have another one at 3, 0. And the last one is at 0. The y-intercept is sitting over there at, we called it -2, so 0, -2. Again, all old news, we've done that before. Then we're going to hit those increasing, decreasing, and constant intervals. So part D is increasing. Part E is decreasing. And part F, that's terrible, stumbling on the alphabet. Part F is constant intervals. So I'm going to abbreviate increasing as INC, decreasing as DEC, and constant is CONST. So that we're not writing on the words. And again, they're intervals using those X values only. So when I start walking along this graph from left to right, picking up the X values, well, I'm walking constant, I'm flat. It's flat line, it's level. So from -infinity all the way until it hits an X value of -1. Oh, that can't be right. I guess we're going to have to call one of these something different because we've already called the intercept. Does everybody see what the issue is? The issue is I have this is -1 and this is -1. That would be 2. That's not a function because it would fail the vertical line test. A single input has 2 outputs. So I guess we're going to label that as -2, 2. That way we don't have to go back and change anything else. Sorry about that. Okay, so it's constant from -infinity to -2. Okay, at -2, it then starts to go downhill. So at -2, we're decreasing, and it's going downhill all the way over to an X value of +1. At +1, you start going uphill again, so that would be increasing. And it's increasing or walking uphill all the way until we had an X value of what, 3.5? Now at 3.5, you start going downhill, and it remains going decreasing or downhill for the rest of its journey. So we're going decreasing from that 3.5 to infinity. Okay, let's make sure everything matches up. So -infinity to -2, -2 to 1, 1 to 3.5, and 3.5 to infinity. So sure enough, we have everything accounted for. We then have a local maximum. A local maximum, well, local maximum, this is not a maximum over here because it doesn't go down on the other side. So it's not the top of a hill, like a bluff, right? You didn't go up to get there. But we do have a maximum here because we're increasing on one side, decreasing on the other side. So we have a local maximum right there at 3.5, 2. And finally, part H asks about local minimum. The local minimum, here's my trough. It's decreasing on one side, increasing on the other. I'm changing directions. So it's 1, -. Okay, so there's another example that also includes a constant interval. And the next thing we need to talk about is symmetry and how that relates to functions specifically. Well, we've already talked about symmetry, so that's nice. That helps us out here. When we talk about functions, we take that idea of symmetry and translate it into an idea of even, odd, and even. So an even function has symmetry, the y-axis. When you look at the picture, you can see our friend the parabola again, which looks like this. Okay, now before when we tested stuff for symmetry, we replaced y. If we're looking for the y-axis, we replaced x with a -x. How does that translate into our function notation? Well, in a function notation test, is going to be if you plug in a negative x, it doesn't change the function at all. We didn't do that before. Well, we did. We just didn't say it from this point of view. So if you plug in a negative x, the function remains unchanged, and that's going to be our test. Okay, well, what about an odd function? So an odd function has symmetry to the origin. We're going to see is a cubic function. And we'll establish this picture pretty much on our next lecture from section 3.4. So this is symmetry to the origin. So if you fold it across one axis and then fold it across the other axis, sure enough, it folds onto itself. So symmetry to the origin. How are you going to remember these two? Well, origin starts with O and odd starts with O. So that makes those guys work nicely. We do have a test. And our test says that if you plug in a negative x, you change the sign of the function. So before, when we tested for symmetry to the origin, we replaced both the y and the x. So, and this is the end result of that. If we plug in a negative x this time, we're going to change the sign of the entire function. Okay, well, what about symmetry to the x-axis? Because we also talked about that. Well, if you have symmetry to the x-axis, it's not a function. And that's why we won't see it from here on out in our course, because it's not a function. So all we have to worry about that would be neither. So it's neither even or odd. So what we're going to do is, given an equation, let's talk about its symmetry and determine if it's an even or an odd function or neither. Got two examples. So this is example 3, part A, and the directions say determine algebraically whether each function is even, odd, or neither. So we have f of x is equal to 3x cubed plus 5. So our test is simple. We're going to come in and find f of negative x. F of negative x would be 3 times a negative x. We're going to cube that. So if I have a negative number and I'm cubing it, it stays negative. And again, you're not touching the exponents at all. You're just dealing with the signs. So this is the result of plugging that in. Now, in order to test, what we really also need is negative f of x. So what's negative f of x? So we're going to come in and just put a negative on everything. We're going to change the sign of the function. Okay. So I've got everything I need. I have the original function. I have f of negative x, and I have the opposite of our function. So the question becomes, if it's the same as the original, it's going to be even. Well, is this the same as this? No. So it's not the same as the original, so it's not even. Okay, if it's the same as the opposite of the function, opposite function, it's odd. Well, this and this are not the same. The sign on the first term is correct, but the sign on the second term is not. So it is not odd either. So this particular function is neither. It has no symmetry to either the y-axis or the origin. So again, what you're going to do your test is take a look at your original function, plug in a negative x, see what you get. Also take a look at what the opposite of x is. If it's the same as the original, it's even. If it's the same as the opposite of the function, it's odd. And if it's a mixture, then it's neither. In this case, it's neither. So it's pretty straightforward until you get to the ones that have fractions or x's in the denominator. Rational functions, they're called. So part B on example 3. We have f of x is equal to x over x squared minus 1. So I'm going to do the same thing again in order to compare things. So I'm going to find f of negative x. So that would be a negative x in the numerator. I'm going to replace the x in the denominator with a negative, and then I'm going to clean that up. So I'm going to move the negative to the bar. Squaring this negative makes it a positive. Then I'm going to find negative f of x. Well, to take the opposite of the function, because it's a fraction, you just put a negative in front of the fraction. So again, I come in and do some comparisons. So if this is the same as this, it's even, and it's not. So it's not even. If this is the same as this one, which it is, and it is off. So because it's the same, this guy is off. This is an odd function. So if we were to graph it, we could use the idea of symmetry and the fact that it folds across the origin to graph it. So in other words, if I grow out what's over there in quadrant 1, I know that the other thing is going to reflect over into quadrant 3. So symmetry can help us graph.